IHES and also from ETH Zurich. She will speak about Brownian loop measure, delta, and length spectra of Riemann surfaces. Please go ahead.
Okay, thank you, Jawad, for the introduction, and thanks for the invitation. It's my great pleasure to speak here about a joint work with my postdoc, Yuhao Xue, who's here. So don't worry if you don't know about these objects in the title. I'm going to introduce them. But after all, the one message I would like to convey today is to show you how we can actually use probability, stochastic processes, to study the geometry of Riemann surfaces. And I will show you one example of one result, which actually we don't know how to do without using the probability. Okay, so let me just get started. Just to put everyone on the same page, we're going to look at the Riemannian surface first. So by Riemannian surface, I mean it's a smooth surface equipped with a smooth Riemannian metric. By Riemannian metric, it just means that it gives you a way to measure the length of each tangent vector, which then you can use that to define the length of each smooth curve. And in this talk, we will consider Riemannian surface without boundary. So if you have a surface like what is drawn here, without boundary, just say, I don't include this boundary curve as part of my surface. You can still have this opening, but it's just that the boundary is not in the surface. Apart from that, we don't make other assumptions. In particular, this surface can have punctures, meaning you can remove some points from the surface. Also, this surface does not have to be geometrically finite, so it can have infinite genus. It can have infinitely many points removed. In this generality, the uniformization theorem says that every such Riemannian surface admits a metric that's conformal to G. Conformal means it's a metric obtained by multiplying this metric G by a smooth positive function, such that under the new metric, this surface has constant curvature either 1 or 0 or -1. And also, this metric is complete. And we actually have a classification. This is about what kind of surface would have positive curvature or 0 curvature or -1 curvature. In the positive curvature, the surface can only be the two sphere, the sphere, the basketball. And for the 0 curvature, that's called a flat surface, it can only be the complex plane, or the complex plane removes one point that's conformal to an infinite long flat cylinder, or a torus, the complex plane modeled out by a lattice group. The translations along the lattice in the complex plane. In anything else, the constant curvature metric has to be minus of curvature, negative curvature. So in this case, those surfaces are called hyperbolic surface. And moreover, this metric will be unique for the surface. And by Riemann surface, it's a surface equipped with a complex structure. And you can also think of complex structure as a notion of telling you how you identify part of the surface as a subset of the complex plane, or equivalently, you can just think structure as assigning a notion of orthogonality at each point of the surface. Or you can think this as the surface equipped with a conformal class of metrics. So here, the metric G and this exponential 2 sigma G, they're in the same conformal class, because one is obtained from the other by multiplying by some function, which is the measurement of the length, but not changing the notion of angle. The orthogonality is being preserved. Okay. These are all classical results about the geometry of Riemann surfaces. Let me give you some examples. Like say this upper half plane. These are the half plane which is above the real line. You can put Euclidean metric on it, dx squared plus dy squared, but for this metric, it is not complete. You can take a sequence, Cauchy sequence for the Euclidean metric, who's converging to the boundary, but the boundary is not included in my surface. So this is not complete. So the constant curvature metric that I was talking about before is this hyperbolic metric. It has complete hyperbolic, it's a metric with curvature -1. And precisely, it can be described as the Euclidean metric divided by the second coordinate squared. And this metric tensor is telling you that a same vector here will be much shorter than if I have to put the same vector near the boundary, because this goes to infinity, y goes to 0, so this metric tensor goes to infinity. So for the same curve coming down here, the length is just getting infinity when you get close to the boundary here. So this is a hyperbolic plane, which is it's also a plane which everywhere looks the same. So by that I mean the isometry group acts on the hyperbolic plane transitively. And the geodesics, we know also how they look like. So the geodesics, these are the curves which locally minimizing the distance. They're given by this either vertical lines or this half circle perpendicular to the boundary. Yeah, and for hyperbolic plane, their behavior looks very differently from the Euclidean plane. For instance, if you take starting from one point and you start going in the straight line, but in different directions. You have two guys like starting at the same point, they're going forward in a straight line, but with different direction. Then their distance between them with time, when time goes to infinity, their distance goes to infinity in an exponential way. That's different from the Euclidean metric. If you go in the straight line, your distance is linear in how much time you spend. And on the sphere within the positive curvature, your distance is bounded because it's bounded by the diameter of your sphere. So this hyperbolic plane has this exponential growth feature. This is a representation in the crochet artist, Diana Taimina, that I found online, that she made this crochet. I think this represent how the hyperbolic plane really look like. It's everywhere, it looks the same, but it's actually going exponentially large. Or this is how nature does it. You have some hyperbolic salad. So this is probably the simplest hyperbolic manifold surface. Let's look at another one. So this is the hyperbolic annulus. If you look at the hyperbolic plane, portioned out by the scaling map. So it's a z to the map some z times some positive number, exponential 2 pi squared over r. And this map is going to identify this yellow geodesic with this part being a fundamental domain of this action. And under the quotient, H mod out by this map, then you get this annulus. So here, the orange line is a geodesic, becomes this line here. Now there's just one, they're identified. Geodesic, and it becomes this middle geodesic of the annulus. And here, this left boundary here becomes this circle. This right boundary here becomes. And these two boundaries are infinitely far. We still have a complete annulus, right? So it's, although it's drawn like on the plane, if you draw it on the plane, it looks like this annulus going from 1 of radius 1 and inside the radius exponential minus r. Recall this r will be related to this r here. It's the same r here. But these two boundaries are infinitely far, because in order to approaching this boundary here on the universal cover, you are here and you have to come down to this point. Yeah, so these are the hyperbolic annulus with the boundary at infinitely far away. And this hyperbolic annulus has one parameter. There's a one parameter family of hyperbolic annulus. They're indexed by this number R. And you can either use this R, or you can also measure this conformal, so index them by the length of this middle curve here. So what the length of this guy is, so this is the length of this green geodesic, and one can compute using this metric to show that the length of this curve is just 2 pi squared over R. Just to say that there's only one conformal invariant. Everything conformal invariant about the annulus will be expressed in terms of the length of this middle geodesic, or R. More generally, a complete hyperbolic surface, recall that it's a surface equipped with the constant curvature metric that's complete, and can be obtained as a quotient of H by a discrete subgroup of the isometries of the hyperbolic plane. And the isometry of the hyperbolic planes, they're all in the form of C maps to AZ plus B over CZ plus D. And we only look at the discrete subgroup that are torsion-free, namely every term in this hyperbolic, in this discrete group does not have a fixed interior point. You don't allow rotation type of map. And then this group acts on H properly discontinuously. You can look at the quotient of H by this group, then you get the surface. And here is one example. Here, and I drew an example of the fundamental domain. And if the fundamental domain contains a part of the boundary here, it comes down, it becomes this this part of the boundary, which is at infinitely far, and this is called a funnel. And sometimes this doesn't contain the interval of real line, but it contains one point, a point of the real line, and that becomes a cusp. And that's a point that also infinitely far. Hyperbolic surface, they're the most majority of the surface, because apart from the sphere, sphere minus 1 point, sphere minus 2 point, and torus, everything else are hyperbolic. And hyperbolic surface, they have a remarkable property, is that for every free homotopy class of curves, of closed curves, and free homotopy just means that two curves are freely homotopic to each other if one can be deformed continuously to the other. And for each free homotopy class that is not homotopic to a point, or so meaning either it's not trivial or it's not homotopic to just a cusp, any other free homotopy class admits a unique geodesic in this homotopy class. In other words, you start with any curve that's not homotopically trivial or homotopic to a cusp, then you can pull it tight, and you would get one element that is the shortest length in this homotopy class. And that geodesic is unique. And this is definitely not true for a flat torus, because if you have a geodesic here, you can slide it around, like on the universal cover. Here on the blue dot, I draw this lattice where you quotient by. If you draw a straight line, this is a geodesic for the Euclidean metric. If you connect to blue dot, it will descend to the surface to a geodesic, closed geodesic. But you can slide it around and to get another geodesic, which is not the same one as before, and they're freely homotopic to each other. So for the flat torus, the geodesics are not unique. Nevertheless, their length is well defined. For the hyperbolic geodesic, because the geodesic is unique, I can talk about the length. And for the torus, although you can slide them around, they all have the same length. And otherwise, in all the other case, so the sphere minus 1 point, sphere minus 2 point, this all the curves are homotopic to a point. And these are cases we don't consider. So the cases that are interested are hyperbolic or the flat torus. And now let me introduce the notion of the multiplicity of a geodesic. So a geodesic, a curve being a geodesic, that's a local property. So if you go through a geodesic and wrap it around several times, it's still a geodesic. A geodesic is called primitive if it cannot be obtained as repeating some other curves more than one times. Yeah, so for instance, here, if I draw this curve, this pink curve, it is primitive. But in this example, I go to twice, and it's not primitive. And the multiplicity is how many times you can obtain, you need to wrap around the primitive geodesic such that you obtain the curve. So for this case, this blue curve, it has multiplicity 2. So being primitive doesn't mean the curve is simple. Like this red curve here, it has a self-intersection, so it's not simple, but it's still primitive. So now let me state our main theorem. So let X be a complete hyperbolic surface, like I draw on the left. P is a set that is closed in X and countable. And X prime is the surface obtained by removing from X this set P. After removing this family of set P, I still get the Riemann surface. And it is a surface that is not the sphere. It's not the sphere minus a point. It's not the sphere minus 2 point. It's not the torus. So it has complete hyperbolic metric. And we will equip this surface X prime with this hyperbolic metric. And since this hyperbolic metric is complete, so the point you have removed, they're infinitely far. So you can think of these points where it's removed under this new metric, they're like very spiky. They're all becoming cusps. And in this result, we don't assume the number of points apart from they're countable, and we don't ask about where they are, so you can put them arbitrarily anywhere. And under this new metric, this surface would look like a hedgehog. Is it very spiky? You can put a trillion of cusps. It's okay. It's a very spiky animal. And now let's take gamma, a hyperbolic geodesic in X. Here, like say this one. We have the following identity. On the left-hand side, I have 1 over the multiplicity of gamma times 1 over exponential of the length of gamma for the metric in X minus 1, and 1 is below. On the right-hand side is the sum. It's summing over all the geodesics in X prime that are homotopic to gamma in the surface X. And on the right-hand side, it's the same functional, but everything is computed using the metric in X prime. Okay, so this is a sum over a lot of geodesics. Like for instance, on the picture here, I have this orange curve is one example. This will be a curve. Is this a geodesic that is homotopic to gamma? You can think of other things. You can wrap around the same puncture more times, 100 times. You can go around several punctures many times. And you can go around some other handle and then wrap around the cusp, and then undo the handle and come back. That also will be. You can think of the cusp, the P that you add, these are just the pins where you put a few pins on your curve, on your surface, and now you just use your orange rubber band to wrap around your surface. And they're allowed as long as if you remove those panes, they will tighten back to gamma. Yeah, so for each, now this is the number of homotopy type on the right-hand side. This is countably many. There are a lot of them. And for each of the homotopy class, there is a geodesic. And that's what is used in this formula here. And our identity says that you have this if this geodesic on the left-hand side will equal to the sum of the geodesics that's homotopic to the original curve, but with the same formula with a different length measurement. If we start with a hyperbolic surface, it works like this. But if we start with on the left-hand side by a flat torus, the only thing you need to do is to replace this function by the area divided by pi length squared, everything measured for the flat torus, for the flat metric. But on the right-hand side is the same functional. Yeah. So that's our main result. Please do not hesitate to stop me if you have questions or something is not clear. All right. Some comment first. If I start with a curve that's primitive as is actually drawn here, this is a primitive curve. Then the right-hand side, all the curves that will be homotopic to the first curve will also have to be primitive. We can actually, it's not surprising because just think a little bit about that. The multiplicity of the curve of gamma prime actually divide the multiplicity of the first gamma. So in this case, the formula would be simplified. You have the 1 over exponential L minus 1 equals to sum of another family of curves with the same functional measured on x prime. And this formula is reminiscent to a famous McShane's identity proved almost 30 years ago. And this is the simplest version of it. It says that if you take this one punctured torus minus 1 point, it's a hyperbolic surface. And if you sum over all the granted simple closed geodesic, now the function is 1 over exponential length plus 1. Then it's always equal to 1. And it looks like very similar to our case if you have just looking to the torus case. But the difference is that we have minus 1 here and the McShane has plus 1. We are summing over all the geodesics that are homotopic to gamma. And he's only considering the simple closed geodesic. And this is very, very different. But still, while the formula we have a minus and McShane has a plus, looks they're so closely related, but in reality, we don't really know why there's these two different, how they're related. Yeah. Okay, so I saw a question, why are there countably many geodesics in the summation in the chat I saw? Yeah, so already all the geodesics on the surface here, it's yeah, so since we actually add only finitely many punctures, so if you just look at all the geodesics on the surface X prime, this will already be countable. Now, if you add uncountably many, then it's not going to be countable. But here, even if I don't look at this curves that are homotopic to gamma, they're already countable. So, but it's always infinite because you can wrap around the puncture like a million times, 10 million times. There's no bound on it. Okay, if there are other questions. Yeah, okay. Thanks for the question, yeah. So this is, I just find the proof of McShane is extremely beautiful and it has nothing to do with our proof, but I still want to show it. What he does is to use the following trick. Have a one-function torus, and he first look at the horocycle around this cusp. By horocycle, it just means that if you look at its lift in the universal cover, say like infinity, this cusp is in the cusp is will be bounded by these two vertical geodesics, and the horocycle is a line which is perpendicular, it's horizontal here. It's some finite length. It doesn't matter where you put it. Now you sample one point uniformly at random. So with a probability 1, you like just pick a point according to the Lebesgue measure. And you start a point, a vertical geodesic flow. You start vertically, so you orthogonally to the horocycle, and you follow this path along the geodesic. So, and it can happen, there's 3 scenarios. The first one is that when it goes, touch itself. In this case, you stop it. Or it goes, you come back to the horocycle. And the third case is that it comes and then it's going to wrap around and getting closer and closer to some closed geodesic. And this thing happens with probability 0. It's very unlikely to happen. Let's ignore that in these 2 cases. And in the first case, we are going to assign a simple closed geodesic. By looking at the loop that it generates, tighten it, you get this gamma. In the second case, you look at the complement of the horocycle and this green geodesic. You chop it off this horocycle, you cut open here, you get an annulus. Right? And annulus is, you look at the geodesic, which is homotopic equivalent to this annulus, and you get one geodesic. It's also a simple closed geodesic. And Maxine just say, what is the probability to see a given curve gamma? And each curve gamma can arise in either way, in both ways. It happens both. And but like you just put these 2 probabilities together, I just look at what is the chance I will see gamma itself, this orange curve. And then compute it, this is exactly 1 over exponential the length of gamma plus 1. And since it's a probability, they have to sum up to 1. And that's how he gets this identity. Okay, you can say this is a probabilistic proof, but it's not really. It's just to say that I kind of decompose this horocycle into different sections, depending on what kind of gamma that it give rise to. So yeah, Maria Mizkani, she used this idea of Mach-Chain. She first generalized this Mach-Chain's identity is almost 10 years later than Mach-Chain's discovery. And she, in her thesis, she used that to explore this full power about the generalized Mach-Chain's identity. In particular, gives her a recursive formula about the V-Peterson volume of moduli spaces of Riemann surfaces. And yeah, that has been really amazing work. And there are other results about identities of the length spectra. So the length spectra just means all the not possible lengths of closed geodesics on the surface. For instance, there are other works about, for instance, Basma Zhang gets the relation between the length of geodesic boundaries of the surface with the length of also geodesic. These are geodesics that are orthogonal to the boundary components. And they're more or less all using the similar idea of decomposing certain geometric quantity into different behaviors and compute these different types of the decomposition and associate that to some other geodesic, length of geodesic. And there are also many other results that I just picked the most representative ones, but there's also many others. then these identities are all about the identities of the length on a single surface. And our result is about length between two different surfaces. And just recall it again here. So far, nothing is probabilistic. And just the proof of this identity comes from facts about the Brownian motion on Riemann surface. I will introduce them. And a very important fact of the two-dimensional Brownian motion, they're conformally invariant. And also the probability of two-dimensional Brownian motion hitting a single point is 0. And also, therefore, two-dimensional Brownian motion hitting a countable set is also 0. And that's in the measure theory, more than measure theory. If you have a countable union, the probability just adds up. And more precisely, we are looking at something called the Brownian loop measure. So this is an infinite measure of loops, and they locally look like Brownian motions. So the Brownian motions on surfaces are very complicated. In the Markov process, they only knows where they are without remembering where they have been in the past, but they just continue the path like with memoryless. And it has been introduced by Greg Lola and Wendering Schwerner to study in the study of the Schramm-Lovener evolution in the complex plane. But the definition of the Brownian loop measure generalizes easily to any Riemannian surfaces, and has been used in many other places, especially in the random conformal geometry, and give you a definition of the law of determinants of Laplacian. And many people have. But let me just first say, for people who are not parabolist, like, what even is this Brownian motion on the Riemann surface? So to define the on the Riemannian surface operator, if the metric is not complete, there's a certain chance that Brownian motion would hit the boundary in finite time. And in this case, I would just stop my process at the boundary. And in two dimension, that's you can make it very concrete. Yeah, so in two dimension, the metric is of the form of the Euclidean metric times some smooth positive function. In two dimension, this Laplacian for this metric is just the usual Laplacian times another function, which is the inverse of the function that you multiplied before. And the Brownian motion for this new metric is the time change of the standard Brownian motion, where standard Brownian motion in R2, it just has two components. If you look at coordinates, they're the two independent Brownian motion. And what does it mean to be a time change? I can write down the exact time change, pathwise time change formula. But informally, it just means that if you don't think about how much time does the Brownian motion need to traverse this path, you just look at where it goes through and in which order they go through. And forget about how slow, how fast it does this trajectory. Then this trajectory is in fact the same for Euclidean metric and for this metric under the conformal metric. So if you take a picture about the trajectory and let it exposure, the time exposed to infinity, and then you got a picture where of the particle has visited, and there's no difference between the hyperbolic plane or the Euclidean plane. So what's actually happening is that in the Euclidean plane, you run the Brownian motion, it will hit the boundary in finite time. But for the hyperbolic metric, the Brownian motion is doing exactly the same thing, but it's just getting slower and slower because the metric is larger and larger. It just takes infinite time to reach the boundary. So in order to make this photo, you really have to turn on the camera for eternity to make this photo. the Brownian motion, why I say this is generated by the Laplace operator? So if you look at the heat kernel of the Laplacian, so exponential t Laplacian, the heat kernel is giving you the distribution of the Brownian motion. So the PT, Z, and W, now you view this as T is a given time interval, Z is the starting point, W is the possible endpoint, and this heat kernel multiplied by the volume form is the distribution of the Brownian motion at time t if it started at Z. For the Euclidean metric, the P, T, Z, and W is just given by the Gaussian distribution. Yeah. Right, so now you know how to do the Brownian motion on the hyperbolic plane. Yeah, sorry, let me just mention that this PT and ZW, it depends on the metric. So everything that would depend on the time, it would depend on the metric. But if something which doesn't depend on time is, say, only encoded property, then this will be conformally invariant. So now, if we know how to do the Brownian motion in the upper half plane, and for the hyperbolic metric, you know how to do the Brownian motion on the surface. If I want to start my Brownian motion from the point on the surface, I will just let it run. I will take a lift to the upper half plane, and then run your Brownian motion here, and then project down, and you get the surface, the Brownian motion on the surface. Okay, now finally, the Brownian loop measure. So now the Brownian motion, I want to somehow make sure they close up on themselves to make a loop. So for this, let me consider WTZ. So X is a point on the surface, T is a time, and WTX is the subprobability measure on the Brownian path, starting from the point X and run for time T, killed when it hits the boundary. If it never hits the boundary, then it's a probability measure. If it's killed at the boundary, so then there's certain probability was going to hit the boundary before time T, and then this total mass will be less than 1. And this is a measure on path. So it's not only know where it is at time T, but it also remembers how it traversed this whole path. So it's a measure on this path. It's a path parameterized by 0 to T. And WT x to y, this is the measure obtained by the disintegration. So it's a measure on path from x to y, run for time t, and such that if you integrate this new measure according to a volume form of the endpoint, you will get back this original, the first metric. In other words, each of this guy is a measure on path, but its total mass is given by the heat kernel. And if you divide by heat kernel, then you get the probability measure. That's the Brownian bridge from x to y. The Brownian motion conditioned to start from x and arriving at y after time t. So finally, the Brownian loop measure, I would choose a time like 1 over t, dt, and then pick a point x according to the volume form, but I now look at this measure WT x to x. Now this is a measure on loop, starting from x, arriving at x, which run for time t, and I integrate over all the possible starting points. I integrate over all the possible time lengths, 1 over t. And this is a measure, it's in measures. It gives you a measure. It gives you a measure on loops. And this is called W on mu xg. This is a measure on loops. And it's an infinite measure. Okay, like already 1 over t itself is not integrable. It blows up when t goes to 0. It blows up when t goes to infinity. It's not integrable. But nevertheless, you can still define the measure. Now for measure, we don't care it to be infinite or not. It's like you can talk about the Lebesgue measure of the real line. It is an infinite measure. The length of it is be infinite, but nevertheless, it as a measure is totally well defined. You can measure what is the length of the interval from A to B on the real line. So it's the same here. It's infinite measure, but yeah, this is how we can deal with the infinities. And this measure on loops has two important properties. First one is a restriction. If I take a smaller surface containing X, but the same metric, then the new Brownian loop measure defined on the smaller surface exactly the loop measure defined on the bigger surface, but restricted to those loops that are contained in X prime. Sorry, there's a prime missing. And the second one is the conformal invariance. If I multiply my metric by some smooth factor, then the loop measure I get, they're exactly the same. If you forget about the parameterization of the loop. Yeah, so this is based on the conformal invariance of the Brownian motion, but also based on the fact we have chosen a very specific factor 1/t. And this 1/t is penalizing big loops and giving more weight to smaller loops. So in the end, the size of the loop doesn't matter. There are smaller loops and big loops, they happen with equal probability. So this is a really two important property about Brownian loop measure. And so now it's have an infinite measure on loops. It's conformally invariant. Now, how about we try to do some topology in it? If we have a Riemann surface, I have this measure loop mu xg. I ask, what is the total mass of Brownian loop in a certain homotopy class, gamma? And the advantage of this is that this is conformally invariant. I don't care about time parameterization anymore. I just look at topological feature about these curves. They're homotopic, freely homotopic to gamma, how much loops there are. And we expect these loops this total mass to be finite. And actually has been computed by Lejeune in the case of a closed compact surface. And he has a big formula for that, didn't simplify it in the end. And we just tried to do it in a better way. And why we expect to be finite? Because here are the small loops. Recall that this is infinite measure because of coming contribution of small loops and big loops. The small loops, they're usually topologically trivial, homotopically trivial. And the big loop, they are topologically too complicated. So they're not going to be homotopic to a given curve gamma. So now we just conceptual way. So basically, you just look at what had happened for a loop to be homotopic to gamma. How does it look like in the universal cover? On the universal cover, I then compute the Brownian motion, and which the mass will be given by heat kernels, which in the hyperbolic plane, the heat kernel, they're nice and they're explicit. We know understanding fully, and we know how to do integration. But conceptually, this computation is actually showing you that in order to compute Brownian loops that's homotopic to gamma, and the gamma will be lifted to geodesic on the upper half plane, and going along the curve gamma, if you take the lift, from this lift to another lift, this corresponds to a scaling map, where the scaling is given by exponential the length of gamma times e. And if I look at the annulus obtained by just quotient out the upper half plane by this only element, the group generated by this element, I get this annulus. I factorize this covering map pi to these two covering map. So the one, you just get the annulus, and the other one is covering from the annulus to the surface. And this covering that's homotopic to gamma will be lifted to a curve in annulus. And every Brownian loop also here, homotopic to gamma, will be lifted to a Brownian loop on this annulus. This Brownian loop measure is conformally invariant. There's only one conformal invariant of an annulus, which is the length of this middle curve, and which is also the length of this curve downstairs. So just from this fact, we already knew that the total mass of Brownian loop downstairs has to be a function of the length of gamma. Which function it is? This needs a computation. I will skip all that. And in the end, what we get is this mysterious function in our formula. 1 over the multiplicity times 1 over exponential length minus 1. So now the proof will be just one line. If you, okay, so if you have a torus, you do the same computation, you will get area divided by pi length squared. And if this is hyperbolic, you get this number. Here we just say, like, let's compute the Brownian loop measure in 2 ways. The Brownian loops that are homotopic to gamma in 2 ways. In the first way, you get this functional or dysfunctional, depending on whether you're a torus or a hyperbolic surface. On the right-hand side, I put some punctures. Now, the Brownian loops, they will be classified into all these different homotopy classes for the new surface. And now I compute the Brownian loops in each of these classes. And now you get this formula. And because of the Brownian loop measure is conformally invariant, these 2 ways has to be the same, as we also know that the loops that would pass through P is actually 0. So there's no loop that with total mass 0 of the Brownian loop that will actually go through P, but the loops that are outside of these punctures, they have the same weight than this loop before. So here, when we applied conformal invariance, we had some tricks that the metric has singularity. You can't directly apply it, but we can carve out some epsilon neighborhood around this piece and to say that in the end, it covers all the loops. So there's some, it's not hard, but conceptually it just says that we have 2 ways to compute the same Brownian loop, one in X and the other in X prime. That's how we get the identity. And that's the end of the proof. So now if we just think back again, what we actually did. Here, when we did this computation of the Brownian loop measure, it is some integral of heat kernel. Yeah, the heat kernel, you get this exponential in the length, etc. But what we actually did is that instead of thinking about the heat kernel, I think this heat kernel is coming from the Brownian motion. And it comes from the Brownian loop measure. And with the Brownian loop measure, I can look at its conformally invariance. And there we really have to know which measure on the loops it is, because we have to forget about the starting point, have to forget about its parameterization. So the Brownian loop measure or the Brownian path themselves, they contains more information than the heat kernel itself, because the heat kernel is the probability that the Brownian motion arrives at a certain point. So it's averaged out information about the Brownian motion. But now we after giving the interpretation of the heat kernel as a Brownian loop measure, then we can do geometric operation on the loops and to show that they're conformally invariant. And therefore, you can also relate the heat kernel into heat kernel of different surfaces, even if the heat kernel, they look very different and for different metric. But we know a priori that because they are coming from Brownian motion, they are conformally invariant. So this is how we actually get this identity. To be honest, we really don't know if there's a way to do it without probability. And these 2 facts about Brownian motion being conformally invariant and also countable sets are polar for Brownian motion. These are really results about stochastic processes. And I'll be very interested in knowing like if people have ways to do it without probability. But at least with the probability, is really a two-line proof about this identity. So finally, I want to spend like 5 minutes just to say about another link to the determinants of Laplacian. That's actually why Brownian loop measure has been motivated at the first place. What determinant Laplacian I'm talking about? So if you have, so here now we restrict to a case where you have complete closed surface with finite genus. There's no fun or no cusp, finitely many handles. The spectra of the Laplacian, they're, you write it down here, and they grow linearly, so you can't define the product. If you want to define determinants, it's a product of the spectrum. So this is Ray and Singer's regularization, zeta regularization. So you introduce the zeta function. It's like the Riemann zeta function, but instead of 1, 2, 3, 4, you replace it by lambda 1, lambda 2, lambda 3, lambda 4. Yeah, now you have a zeta function. They grow linearly, so their behavior is very similar to Riemann zeta function. And now this is a zeta function which can be analytically continued to the neighborhood of 0. And the determinant of Laplacian is defined by minus zeta prime at 0, which formally, if you take a derivative in S and evaluate at S equals to 0, you get log of the product. And that's why it's defined as a log determinant of Laplacian. And having been used a lot by physicists to whenever they want to talk about the determinants of Laplacian. And it was observed that by Lejean, Jubeda, that the total mass of Brownian loops, they're supposed to be describing the total mass here, mu m. The total mass of Brownian loop in the surface M is given by minus log of the determinants of Laplacian. Where on the left-hand side, there's zeta regularization. On the right-hand side, we know that's infinite, and it doesn't make sense to say this identity. But it has a way to make precise. Remember, we said that the total mass of Brownian loop is infinite because there are contribution from small loops and also contribution from big loops. And for small loops, so this little t and big T, if I just look at the loops of total length projective variation between these two numbers, then you know how they blow up when little t goes to 0 and big T goes to infinity. If you remove this blowing up term, this blows up and this blows up. After removing those, you get this constant term, which is exactly given by log determinants of Laplacian. So that's very satisfactory, but we want to look at other ways to renormalize this and get determinants of Laplacian, but in the way like classifying the Brownian loops according to their homotopy class. And this would get rid of the small loops if we just look at the homotopically non-trivial Brownian loops. It gets rid of the small loop. And about the big loops, well, we know that it's going to be infinite. And why is infinite? We can see it from this way. We classify those Brownian loops according to the homotopy class. And the total mass of Brownian loops we're given by is a function of the length of the geodesic representative. Now, if we look at the total numbers of geodesic of length less than L, so this is definition, gamma is primitive with length of gamma less than L, and the counting of this number behaves very much like prime numbers, log of prime numbers. That's called prime geodesic theorem. And their counting has this expansion, which depends on small eigenvalues of the Laplacian. And the first leading term is the Lie function defined here. Evaluate exponential L. So asymptotically, this is exponential L. So that's how many prime geodesic there are less than L. Remember, the Brownian loop measure contributes to 1 over exponential L, basically. And therefore is not summable, which we already expected. So a naive way to say, okay, if I want to take the sum of the Brownian loops, I would just look at those who are homotopically equivalent to non-primitive geodesics, and those are homotopic to primitive geodesics. So if you just take the integral of 1 over x minus L minus L dnx of L, this would counting all the Brownian loops that's homotopic to prime geodesics. But now we know that's infinite. So now let's just renormalize it by some function, the leading order term. So now the renormalization, which you remove, doesn't depend on anything. It's just 1 over L exponential L minus 1 times dLi of EL. So this is the same renormalization for any loop, for any surface. But now this makes it finite. And what we show is that this log determinant Laplacian is again written as some area. The area is just a function of genus times some universal constant plus another universal constant, and then a renormalization of the total mass of Brownian loop. Now they're classified using their homotopy class. And so the proof of it is again using the Zellberg trace formula, which is in fact relating the spectra to the length of geodesics, which we just interpret everything in terms of Brown.
I cannot hear you, Yilin.
Two applications. One is the identity on the length spectra of the surface. And the other one is we get the renormalization of the total mass according to the length spectra and express log determinant of the of Laplacian in terms of the length spectra or in terms of Brownian loop measure. Yeah, and there are a lot of other open questions that yeah, I don't have time to really talk about, but thank you very much for your trying to pronounce this. Yeah, thank you. Yeah.
Thank you very much for your nice presentation. Oh. You are written in Persian. تشکر میکنم. Yes.
Yeah, well, copied online. Like I don't, yeah, I can't write it either.
Okay, thank you. Are there any questions or comments? Actually,
There's one in the chat.
no, I cannot see.
No, that's not the question. Thank you for, yeah.
If it's okay, if it is not the case, let's thank Yilin once more for the nice presentation. I hope sometime we could have you in Iran in person.
Yeah, well, I hope so. Yeah.
So, mm, mm.